This conference will now be recorded. This conference will now be recorded.
Very good morning, students. We have recently learned about electrostatics. Or what was electrostatics? In electrostatics, we have learned some physics when the charge was static. Charge was stationary or static. Okay, or stationary. All right. So this was the topic electrostatics, where charge was stationary or static. In this case, what we have learned? We have learned electric field created by stationary charges, potential created by stationary charges, forces that acts between them, etc., etc. We have learned, and many more things we have learned. So today, what we are going to start is the current electricity. So what is current? And the current is the charges in motion constitute an electric current actually. Okay, when charge is flowing or in motion, that constitutes electric current. So this is a very crude definition. We can learn it factually when we as we go along with the discussions today. So in case of static charges also we see some kind of flow or motion of charges. So electric current is flow of charges, flow of charges, flow of charges. So there could be two kind of sources of flow like electric current. One is natural source of current, and other one is the artificial source. The current we are using in our household and offices, etc., actually is produced by human being. Okay, not naturally occurring current, electric current. So what is the source of naturally occurring electric current? An example is lightning. So during lightning, a huge amount of charges flow from the clouds to the earth through the atmosphere. So this is a naturally occurring current. This actually a huge amount of charges flow through the atmosphere, and where to where? It goes from cloud to the earth. Earth is considered to be the sea of charges, sea or ocean of charges. So as much as possible we can add charges to the earth, or we may take it also, but charges will never come in short in the earth. Okay, so there will be no lack of charges. So it is kind of ocean. Okay, generally earth is taken as zero potential. All right, so those things we'll learn as we go along. So this is natural source of electric current. But what is the problem here? Can you use this current what is flowing through the atmosphere to the earth during lightning? Can you use this current in our household activities or appliances? Can you use? No, we cannot use household devices this kind of current, because see, from the cloud suddenly huge amount of charges will flow to the earth. Okay, huge amount of charge will flow to the earth. This is actually a sudden or unsteady, I can say sudden flow or unsteady flow. I can give you a very simple example. Suppose you are in the shower. You are in the shower, and you know water is coming very like, see, suddenly some water comes and then it stops. Is it very useful to take a shower this with this kind of flow of water through the shower? Neither will get any like satisfaction, or nor it will be very useful. So we need a steady flow of water to take a shower, right? So similarly, if we want to use electric current, the electric current has to be a steady flow of charges. Okay, it should be a steady flow. I should get a steady flow, okay, or continuous flow. So that's why the current we get naturally during lightning, we cannot use that in our household devices. Okay, but obviously human beings are very curious and very intelligent to make everything use in their life. So research is going on how to catch this current or this much huge energy during this lightning, how to catch hold of that and then make use of in our life. Okay, make use of that energy in our life. However, we'll see. So we have seen that steady flow of charges, steady flow of charges that constitutes steady current, and that we see in electrical circuits, isn't it? Okay, that we see in the electric current circuits. So what is electric circuit? And see this case, see, I was just talking about steady flow. We'll just talk about later also, but still, let me just give you one glimpse of the current actually what we get through our circuits. Generally, in a conductor, there will be positive ions and electrons, and conductors are characterized by free electrons. Okay, conductors are characterized by free electrons available in the conductor. Okay, in the bulk of the conductor, there will be some electrons or outermost electron of the atoms or bit. So those electrons actually are getting free to move throughout the bulk of the material. Okay, if I have a conductor like this, so there will be some electrons which can randomly move through the entire bulk of this conductor. Okay, so if I take, okay, so for the timing, let us just consider that there are charges, positive charges and negative charges. Okay, positive charges and negative charges. I'm writing Q negative. If I take a cross section kind of this, which is perpendicular to the flow of the charges. So if some charges, see, charge can flow randomly any direction. Okay, I'm just considering, suppose this is the forward direction, and suppose Q plus is the charge, okay, which flows in a particular time interval t. Some plus Q charges flow in the forward direction, and some Q negative charges also flow through this or across this cross section, in time during this time interval 0 to t, say. Okay, so as this positive and negative charges flow in time t during this time interval t, since there are positive and negative both charges are there, So how much is the net flow? Net flow we need to know. Net flow of charges. We'll see net flow of charge. So what is net flow of charge? Let us say that is Q, and that could be written as Q plus minus of Q minus. Okay, so this net flow of charge is happening during T interval of time, and the electric current actually is defined as this net flow of charge per unit time, per second you say. So the electric current is defined like denoted by I, and it is defined as Q by T. This is the net flow of charge. But this is kind of average charge. There is another definition that will just, so this is kind of average, like average velocity. Average velocity is the total displacement d by total time interval. And also we have instantaneous current, right? We have just instantaneous velocity, that is d. Suppose this is s, suppose this is s distance, and ds by dt, this is instantaneous, and we take some time, this time t. Okay, just a minute. We know average velocity, let us say this time delta t interval. So this velocity, instantaneous velocity, can be written as limit delta t tending to 0, this d, this also let us say delta s. So delta s by delta t. Okay, and see, according to the definition of derivative, it is ds by dt. So this is instantaneous velocity. Similar way we can define current, average current. So simply I average, if I say average current, that is total net charge flow by time interval. Okay, but same thing, like if I write instantaneous current kind of that, then I have to write dq by dt. So these are simple definition of current. Okay, so what is, see, since we have already learned what is current, I can actually take the, like we can understand what is the unit and all. We can just write down what is the unit and all. Okay, so unit dq by dt or q by t, this is actually coulomb. Q is in SI unit, coulomb per second. This is written as ampere. Ampere denoted by capital A or small amp, we should write. Okay, so unit is ampere. All right, so let us see. So an electric circuit, now we'll see an electric circuit consists of active and passive elements. So what are active elements? Active elements are those elements which supply energy to the circuit. Okay, supply energy to the circuit. Okay, so for example, battery or cell. So these are actually active elements, and there are some elements which are passive elements. I'll write it here, passive element. Okay, so there are some passive elements also. I'll write this in short so that supply energy, and examples I'll write in bracket. so that I get some space here. Example, battery or cell. Okay, and this actually consumes energy. Okay, passive element consumes energy or stores energy. Okay, stores energy, and these are actually capacitor stores energy, right? Capacitor, then inductor, they store energy, but resistors, they dissipate or consumes energy. Okay, so these are few things to know about electric circuit. Now I had already written what is electric current. So a steady flow, we'll see a steady flow of electric charges. Okay, and mathematically if you define, there are two. This is kind of average current. Okay, average current means total current or total net current flowing in certain time interval divided by that time interval, and kind of instantaneous current that we can define as dq by dt, that is the rate of flow of charges. Okay, and we have learned already what is definition, what is the unit and all we have obtained already. So this is the definition of electric current. See, this could be used, see, or question may come in other way also. Suppose the current is given and time is given. So how much charge has been flow, like how much has charge, how much charge flow has happened during the time interval? How can we find out that? See, if I want to know what is the total charge flow happened, so that I have to do in this way. I d t. Okay, suppose time t1 to t2 during this time. Okay, so I mean to say you have to do the integration q from the 0 to q. Okay, so this will give you the total amount of charge which was flowing during the time interval. Okay, so I could be coming out dt integration over dt, or idt, let me keep it inside itself because we don't know whether current is always constant. Current may vary also. All right, so we'll take a few examples related to this. Let me give you some example here. I'll write the problem here, numerical problem. Example number 1 say, the current in a wire varies with time according to the relation what is that relation? I is equal to, okay, I is equal to 3.0 a ampere plus 2.0 ampere per second whole into time. Okay, this is the thing given. Now question is, How many coulombs of charge pass? I'm just writing how much coulomb of charge. Okay, how much coulomb charges pass or charge pass? How much will charge passes across the section of the wire in the interval across the section of the wire between t is equal to 0 and t is equal to 4 seconds. Okay, so this is one question, and another question is what constant current would transport the same charge? Current would transport the same charge in the same time interval. Okay, so this is the question. The current in a wire varies with time according to the given equation. Now, how much how much charge passes across the section of the wire between t is equal to 0 to t is equal to 4 seconds? Okay, I'll just take the help of the next page. So I have been given current 3.0 ampere plus 2.0 ampere per second into t. Okay, now see the definition of the charge flowing or charge passes is integration I dt and time t1 to t2 interval. Okay, so here it is given, the time is given 0 to 4 seconds. So in this case we'll just write the this much plus 2 0 into t base 1 into dt. So this is the integration we have to do. So with this there is no t term, but during integration one t term will come. So 3t plus 2 t square by 2, and there is a limit 0 to 4. So 0 means everywhere it will be 0, and see this is 4 means 3 into 4 plus this to goes off, and this will be obviously in coulomb. Okay, this will be coulomb. So this is 12 and this is 16. So this will be actually 28 coulomb. We can write down coulomb as a capital letter also. So this is coulomb like this. Okay. So we have got what is the charge flowing during this interval of time. Now the question is, second part, what constant current would transport the same charge? See, that means you know what constant current. I have to write I is equal to dq by dt, or I know the dq have, like this is 20 coulomb. divided by, this is time, second. So how much it was? 4 seconds. So it will be some 7 ampere. So 7 ampere current during 0 to 4 seconds. If it for like if it is a steady current, then I can write dq by dt. Okay, dq by dt. So and that is here actually 7 ampere. The dq by dt is 7 ampere, or the steady current which can flow during this 0 to 4 second and can deposit the same charge. Okay, same charge, that is 28 coulomb. Okay, so this is about numerical problem. I think there is another numerical problem. We can do it. See, sometimes you may be given how many electrons. Suppose here I can add this part after this. How many electrons, or how many positive or negative charges passes? Electron, how many? So pass across the section of the conductor. Where? So how do we write here? So Q is equal to, that is N into E. So from here we can find out how many charges or how many electrons have how many electron passes through, or how many charges. This we have to do. So in this case, oh sorry, how many number? We need to find out the number. From here I can find out N. N is the integer number. So Q, total charge, divided by E. E is the electronic charge or protonic charge, you can say. So this will give you the number of charges flowing. Okay, so we have seen that the charge, if we want to calculate charge, we should write I dt integration, right? Some tu1 to t2. So this is the integration. What does this mean? If suppose there is a current versus time graph like this. Okay, I'll just take up the example. Let me. So suppose this is I here and this is time. Okay, so what is the charge flowing in this? How do we find out? I dt, that means the area under this curve. So I dt means the area under the curve. So this area under the curve is giving the amount of charge. So here there is a simple problem, numerical problem. We'll just do it. Current passing through wire decreases linearly from 10 to. So this is the graph. I'm not writing the language of the problem, but I'm just reading that language or saying that language in mouth. So current passing through a wire or a conducting wire anyway, and that current linearly it decreases. Current decreases linearly, as you see. The current is maximum here and it is linearly decreasing. from 10 ampere. So here it is actually 10 ampere. From 10 ampere to 0, so this is 0 ampere. So 10 ampere to 0 ampere, it changes. Then, and that happens in 4 seconds. So this is 4 seconds here. Oh, sorry, this is 4 seconds. Okay. Current versus time graph we have to see, and the total charge flowing through the wire during the given interval. Total charge. Question is total charge. Total charge flowing through the wire. So flowing through the wire during 4 seconds. So the interval of time. So that is actually the area under the curve. In this case, how to find out area under the curve here? So area of this triangle will be half base into height. Half base is 4 and height is 10. Half base height, this much is the area, so that means 20 is the area. So this is nothing but the charge of amount of charge flowing. This is actually the charge flowing. Okay, so this is about current and related numerical problem. Now we'll see the same current when it flows, or how current flows in a solid conductor. In a solid conductor, as we have discussed, see, solid conductor, actually there could be two kinds of conductors. So one is actually electrolytic conductor and the solid conductor. Here we are choosing to discuss electric current through the solid conductor. So solid conductors, suppose if I take a piece of conductor, it has a huge number of positive ion cores sitting. These are relatively massive particles, massive. They cannot move from one place to another. These are that's why these are called lattice. They are sitting at that particular position according to the symmetric consideration. So these are called positive ion cores. Positive ion cores or positive ion cores. Positive ion cores. Now, conductor has a property that conductors have the free electrons to move around. Okay, free electrons. Again, you should not be confusing with free word. Free means they will not be able to come out of the surface of the conductor, but inside the bulk of the conductor they can roam around like this and all very randomly. And during the motion, random motion, see these are the random motion of electron. When I talk about electric current in a conductor, as I said, positive ion cores, they are massive. They are massive in mass, massive in size, cannot move. They cannot move. They cannot move. So massive, this ion cores or positive ion cores, they cannot move. That's why electric current, okay, I'll write here. Electric current electric current in a conductor conductor electric current in a conductor arises only due to electrons. Only due to electrons. Okay, so only due to electrons we get the electric current in conductor, because the positive ion cores or the atoms, they are actually very massive and they cannot move from one place to another and doesn't contribute to the electric current. Okay, now we'll see what happens in general in a conductor, inside a conductor. Okay, inside a conductor when electric field is not applied. See, there are electrons, obviously free electrons are there. How is their motion? How is their motion? The motion is random. Okay, so inside a conductor, if I have many electrons which are moving randomly, and during the random motion there are, see, these iron core brothers are also sitting. They are sitting at their position. They are neither moving, they are not able to give sides also to these electrons. Okay, so obviously there will be collision with the electrons during their random motion. So first of all, when they are moving randomly moving in the sense they are both magnitude of the speed, magnitude of their speed and direction, or I can say velocity, magnitude of the velocity and direction both changes. Velocity and directions both changes very randomly. Not only the magnitude, not only the direction, both changes randomly. So because of this random motion, see, if I take the average speed, see this random motion, the speed actually is very high due to this thermal motion, 10 to almost 10 to the power 5 meter per second. This is the speed, random motion, the speed during random motion. Okay, speed during random motion. But this much speed is no work actually, because This is random motion. If we take the average of this velocity, this gives 0. Okay, this gives 0. Average velocity is 0. Okay, but see this scenario will change. This scenario will change if see first of all, if the electrons are moving randomly, will you get any net flow of charges through any cross section? Through any cross section, we will not get any definite net flow of charges through any cross section of the conductor in absence of electric field. So this is in absence of electric field or potential across it. Okay, so no current is obtained during that time because of the random thermal motion of the electrons. Now if I apply a suitable electric potential across the conductor, see this is the conductor, actually conductor, same conductor. If I just take the same conductor and just connect to a battery or cell, as soon as the circuit is closed and the conductor is connected to a battery, providing positive potential or providing a potential difference across the length of it, then this electric field, see this due to this electric field, the electric charges, they will have a definite net charges flowing through or flowing across the conductor. Okay, so when an electric field is applied across the length of the conductor, then only the steady or net flow is getting established. So net flow of charges happens then. Okay, net flow of charges happen when so net flow of charges will constitute a current. Okay, and see, you can see one thing here, the electrons, these are negative charges, so I can take this as an electron. So they are moving, see, from lower potential side to higher potential. This is low potential, low to high. So electrons always move from low potential to high potential, whereas the current is taken as the direction of flow of positive charges. See, direction of flow of positive charge and negative charges is exactly opposite. So generally or conventionally, electric current is taken, direction of electric current is taken as the direction of electric current is the direction of flow of positive charges. Direction of flow of positive charges. Alright, so direction of flow of positive charge is taken to be, say, if there are positive charges movable, so they could have gone from high potential to low potential. So the electric current also flowing from high potential to lower potential. Okay. All right. See how it happens, how this steady flow gets established here. Okay. So that establishes due to the electric field across it. How is it so? See, when there is an electric field, so the electric charge will experience a force due to the electric field, and that is given by Q into E, or here it is E minus E. Sorry, minus E into E. So this is the force which electrons actually experience in the presence of this electric field across it. Okay, and if each electron has mass me, then I can write the acceleration due to this electric field is produced in electron. I'm sorry. Acceleration will be force by charge. Force by mass. Okay, this is the acceleration due to this. So this is the acceleration that experience those electrons, experienced by those electrons. But one thing is very, very surprising, that even though electrons are experiencing this much acceleration, the electrons will not be accelerated through the conductor. Why? It is because of the collision. During the collision, they, like, there will be various collisions, like multiple collisions during their passage through the conductor. So there will be multiple collisions, and during that collision, each collision it will experience, sorry, each collision it will actually, during each collision it will lose its kinetic energy, and also after the collision the speed or the direction and magnitude of the velocity changes. Okay, okay, so this is the acceleration it experience its electrons. Now suppose there are n number of electrons in a conductor, n number of electrons are there, right? And all of them are doing random motion, absence of electric field. Then what will happen? Okay, so I think the acceleration it experience is this, but this acceleration, say during the random motion, what happens? There are positive ion force, right? Sitting here, with the specific periodicity, that is called lattice. Okay, so while moving randomly, this random motion, suppose the velocity of ith particle, if there are n number of particles, and among them ith particle I have taken, and that ith particle, see, I can be 1 2 3 goes up to n. So suppose this is the velocity, instantaneous velocity of each electron. Okay, each electron, instantaneous initial velocity, let us say, of each electron. So since it is, so if I take this average of this, it will be 0, because this is random velocity. Okay, random velocity. Now we have got this acceleration, and this velocity, initial velocity vi, is already there. Due to this, it will actually move in a straight line, and see, during like there are successive collisions. Suppose there is these are positive ion cores. One electron comes like this, it collides with this, and then it collides with this. So this is electron. After the, so the time interval between successive two collisions, okay, between two successive collisions is T say, and Ti is the time it takes like by individual particles, okay. So we have to actually, and also the individual electrons, they takes very random time between successive collisions, not only T, okay, it can be different. So we have to actually consider suppose these are two successive collisions like this. So we need to consider the case between two successive collisions, okay. So the time interval or time elapses by an electron between two successive collisions is actually called free time, and the distance is covered is called free path. Free path, it is called free path. The distance is covered during two successive collisions is called free path. So we have free path, free time also, okay, sorry. So free path is the path or distance traveled by an electron during like during the time interval between two successive collisions. So free path is there, free time is there. So free time, free path, okay. So the velocity with which this particular, so during the collision, see this free path is actually, free path is a straight line. We take generally straight line, okay. Free path is taken as straight line. Okay, so all right, so I think this will stop it here for today. Next day we'll take up the remaining portion, like relaxation time, etc. will take up in the next class. Relaxation time and the derivation of drift velocity will take up in the next class, okay. So thank you for your attention. Bye for today.